Welcome to the deep dive. We're here to sift through complex information and pull out the really essential stuff for you. Today, we're tackling something that sounds maybe a bit niche, a bit technical at first glance. It's called the ESR function block. But honestly, stick with us because this little piece of logic, it's actually fundamental to how tons of automated systems work, things all around us. So ESR stands for event-driven Bestable. Think of it like a very smart, very precise digital switch, one that remembers what you last told it. Our info today comes from a bunch of documents looking at industrial control programming standards, particularly the IEC 61499 standard. And our mission really is to get to the heart of how these systems manage states, why understanding this one seemingly small component is, well, pretty critical if you want to be genuinely clued in about automation.
Yeah, and you're right. Event-driven bistable does sound quite technical, doesn't it? But if you think about ESR, just picture a really simple memory element. Or maybe, yeah, a specialized switch that just holds onto its last command. The core ideas behind it are actually surprisingly close to things we use every day, like, a standard light switch. It stays on or off until you flip it again. It's about predictability, state memory.
Okay, let's unpack that then. Be stable. What does that actually mean in, simple terms? And why is it so key for the ESR?
Right, so be stable just means it has two stable states. That's it, basically on or off F, or true or false in digital terms. And like that light switch example, once it's set to one state, it reliably stays put. It won't just randomly change. It needs a specific command and event to flip it. The ESR block is a core part of this IEC 61499 standard, which you see a lot in industrial control, precisely because it offers this really robust two-state memory. Its main job. Trigger some action when, say, event A happens, and then get reset back when event B happens. Very reliable.
Got it. So it remembers something and acts only on specific triggers. Sounds clean. Actually, the source material had this great analogy, Holtz, Bolter, Schulter, a wood splitter switch. And the point was, ein Schalter, einschalten. One switch turns it on, and ausschalter, a different switch turns it off. It really helps picture that straightforward, on-off, true-false behavior.
That's a good one. And it ties into something pretty interesting from the sources, a subtle detail about how standards evolve. See, in the, let's say, older IEC 61131.3 standard, there was this clear difference made between SR blocks and RS blocks. SR meant set priority. If both set and reset signals arrived at the same time, set would win. RS meant reset priority.
Yeah, so a way to handle conflicts.
Exactly.
Yeah.
But in the newer IEC 614991 standard, the one we're focused on, that distinction is gone. SR and RS basically do the same thing now. The only difference is which input pin is called S and which is R. They just swap the inputs.
Huh. Why not do that? Just simplicity?
Simplicity is a big part of it, yeah. It was a deliberate design choice. It makes the basic building blocks more uniform.
That simplification, getting rid of the SR versus RS priority thing.
Yeah.
It's actually really interesting. Is it just simplicity, or are there maybe other benefits, like in distributed systems, maybe less chance for error or easier debugging?
Oh, definitely. It's more than just making it look simpler. It absolutely reduces complexity when you're designing and implementing systems. Think about distributed control, like you said. Maybe different parts of a factory floor talking to each other, having a single unified behavior for these basic memory blocks. That means less ambiguity, fewer potential mistakes in the logic, and yes, it makes debugging easier down the line. It standardizes how these things remember state, which is a huge plus when you might have hundreds, even thousands interacting.
Right, that makes total sense, especially at scale. Okay, so that covers what it does, but now I'm really curious about the how. Can you sort of walk us through the internal structure? How is the smart switch actually put together inside?
Sure thing. So the ESR is formally defined as a basic function block, or BFB. That's the terminology in IEC 61499. And any BFB, like our ESR, has two main parts. Its interface, how it connects to the outside world, and its internal logic, how it actually works. Let's look at the interface first. It's got two main event inputs, S for set and R for reset. Pretty straightforward. An event arriving at S tells the block, set your output variable, which is called Q, to true. And an event arriving at R, that tells it to set Q to false.
Okay, S sets it true, R sets it false, and Q is the output state. Got it.
Exactly. Q is just a Boolean true or false. But here's a really critical part of the design, something key to 61499. It also has an event output. It's usually labeled EO, and this EO output fires off an event only when the value of Q actually changes.
Okay, so not every time S or R comes in, only when Q flips.
Precisely. It's not just remembering the state, it's actively signaling when that state has changed. This explicit announcement is, well, it's fundamental for coordinating different parts of a distributed system. Think about the alternative. Other blocks would have to constantly ask the ESR, are you true yet? Are you true yet? Are you false? That's called polling, and it's inefficient.
Right. Lots of wasted messaging.
Exactly.
Wow.
Instead, the ESR just broadcasts, hey everyone, my state just changed, but only when it actually happens. That makes systems much more efficient, much more scalable, especially in, complex industrial settings.
So it's not just a switch that remembers, it's like a switch that only taps you on the shoulder when it actually flips. Which, yeah, if you have thousands of them, that sounds way better than checking each one constantly. That's clever.
It really is. It's a core principle of good, event-driven architecture.
Okay, so now for the internal logic. How does it decide when to change Q and fire EO? This is controlled by something called an execution control chart, or ECC. You can sort of picture it like a little state machine or a flow chart inside the block. It dictates exactly how it behaves, ensuring it's predictable.
A state machine inside the block itself.
Oh yeah, essentially. A simple one. It always begins in a state called start, just waiting. Then, if an S event arrives on the S input, the ECC transitions the block to the set state. And associated with that set state is a tiny piece of code, an algorithm that just says Q, true. And because Q changed, it also triggers the EO output event.
Okay, S event master set state def Q becomes true EO fires.
Perfect. Now, it stays in that set state. It won't just flip back on its own. It needs an R event to arrive on the R input. That causes a transition to the reset state. And the algorithm for the reset state, just Q, false. And again, because Q changed, EO fires.
Our event reset state PQ becomes false EO BO fires, and then it stays false until another S. Exactly that. From reset, the next S event will transition it back to set, and the cycle continues. This strict, event-driven movement through defined state start, set, reset is what makes it so reliable. It can't get confused or stuck somewhere in between. That's vital for, safety and stability and automation.
That internal flow chart, the ECC, really locks down its behavior, makes it incredibly predictable, which must be absolutely critical for industrial stuff. So bringing it all together, what does this mean for how the ESR block actually behaves, like in a running system?
Well, in practice, it behaves exactly like that simple flip-flop we talked about. It's controlled entirely by those incoming S and R events. S sets Q to true, R resets Q to false. That's the memory part. And crucially, whenever Q actually flips its value, bang, the EO event goes out, signaling that change happened. That's the event-driven part. Now, this might still feel a bit abstract, like, okay, an event-driven flip-flop. Why should you listening now really care about the nitty-gritty of this one industrial block? And the answer is, this simple but really robust mechanism is a foundational concept. It's one of the absolute basic building blocks for creating complex automated behavior. It's fundamentally about how machines can reliably remember information, make simple decisions based on events, and react intelligently to things happening in the real world. That underpins so much automation, ensuring it runs smoothly, predictably, and importantly, safely.
Okay, let's make it even more concrete. Let's bring it home. Where would we actually see something like an ESR block, or at least this logic, being used out there? In factories or elsewhere?
Oh, absolutely in factories, but the principle applies more broadly too. Anywhere you need that reliable two-state behavior, the ESR concept fits. So one obvious use is just simple state storage. Like, you need the system to remember if a particular machine is currently running true or stopped, false. Or maybe if a safety guard is in position, true, or open, false. The ESR just holds that state.
Okay, like a digital status light memory?
Pretty much. Then there's its role in event-driven control logic. Modern automation is often designed to react very specifically to discrete events, a sensor triggering, a button being pressed, a timer finishing. The ESR is perfect for managing the state changes that result from these events. And because it sends that EO signal, it can tell other parts of the system, okay, my part is done, the condition is now true or false, which ensures everything happens in the right sequence.
Ah, so coordinating steps in a process.
Exactly. Like a digital baton pass. Okay, the part is clamped, teacher read, now you can start drilling. That kind of thing. Maybe most critically, you find this logic used heavily in safety functions. Being able to reliably store critical states like emergency stop activated, true you, or ensuring a system can be put into a safe state and reliably reset, that's paramount. The predictability of the ESR contributes directly to making machinery and processes safer, helping prevent accidents because components respond exactly as designed. Every time.
Right, you definitely want your safety logic to be rock solid and predictable. No ambiguity allowed there. Okay, so We've really dug into this ESR function block. It seems like such a small thing on the surface, doesn't it? But it's clearly a real cornerstone of how modern industrial control works. It's kind of a neat example of how really complex automation often relies on these incredibly simple, super robust, event-driven building blocks, things that just, well, work every single time. It's about building reliability from the ground up.
Absolutely. And if you zoom out a bit, connected to the bigger picture, the ESR block is a perfect illustration of the whole philosophy behind IEC 61499. That philosophy emphasizes flexibility, modularity, reusability. It shows how you can construct these incredibly complex systems, think an entire automated warehouse, or maybe a smart power grid from relatively simple, well-defined, reusable components. It's almost like building with very precise, very reliable digital Lego bricks. You get both adaptability and that crucial predictability.
That's a great way to put it. Digital Lego bricks for complex systems. So maybe something for you, our listener, to think about. Next time you interact with any kind of automated system, could be your smart speaker at home, could be watching a robot in a factory video, could be anything really. Just take a second to consider the layers upon layers of precise event-driven logic working away behind the scenes. Logic very much like this ESR block we've been talking about. Logic that makes it all possible. And maybe ask yourself, what other really simple, fundamental building blocks like this do you think are underpinning all the complex technology around us, the stuff we often just take for granted?